Part 3 of heat involves calorimetry. So this is the process of measuring the amount of heat released or absorbed. So when you think about that, that's heat gain or heat lost. So a reaction is exothermic if it releases heat, like exit, and endo if it absorbs heat. The total heat lost will equal the total heat gained, and the net heat is zero. Heat always flows from high temperature to low temperature until all elements reach an equilibrium. So we're going to be putting ice inside of glasses or mixing two liquids together and letting the whole thing settle out at a new temperature. That's what calorimetry is. So for instance, here's a little problem. We have a calorimeter. It's made of aluminum and it contains water, as shown. The water and the cup have the same temperature of 18 degrees. And imagine a mass of unknown material is heated to 97 degrees and then added to the water. Alrighty, so after thermal equilibrium is reached and everything has come to the same number, the temperature is 22 degrees. Ignoring the small amount of heat gained by the thermometer, find the specific heat capacity of the unknown material. So this is a calorimetry problem, and we're going to set it up heat lost equals heat gained. And it doesn't really matter what you're being asked to find, because once you fill out those whole equations in heat lost equals heat gained, and then you expand them and fill in what you know, the only thing left over will be the thing we're looking for, which is the specific heat capacity of the unknown material. So once you do get the specific heat capacity, you could compare that to tables and say, oh, that unknown metal must be aluminum, or it must be whatever, steel or something. So heat lost equals heat gained. So lost is the unknown material, gained is the aluminum and the water. So you've got MC delta T equals MC delta T plus MC delta T. Now you might have a heat phase in here. If, for instance, ice was dumped in here as well, you would have the ice would have to go in the heat phase. First, you'd have to have, say, minus 10 to 0 is an MC delta T, and then it would be an MLV on there too. But this one is not like that. So this is a material, MC delta T equals MC delta T plus MC delta T. Easy enough. You expand it, you put in your changes of temperature, and we are going to leave all of our changes of temperature as positive numbers. So it had gone down 75 is your delta T, 4 and 4. So the final temperature was 22 for everything. So when you think about it, the unknown material went from 22, 97, minus 75, but we're going to be using 75 over here. We're doing that because heat lost would be, you could follow your negatives all the way down through here, and our original equation could have been 0 equals heat gained plus heat lost. And then the heat lost would be negative. It would all work out. So we are not going to do that. We're going to keep our temperatures as positive, and we are going to use our absolute value of our change in temperature, and we're going to have lost equals gained. So here's another example. We've got ice at 0 degrees is placed in a cup containing lemonade. And now for the lemonade, we're going to use the same specific heat of water, because it's going to be basically the same thing. It's water with some sugar and flavor in there. So after the ice and the lemonade reach an equilibrium temperature, some ice still remains. So that's a little clue right there. So you're putting ice in the lemonade, and it's going to melt, and some ice still remains, which means your final temperature is 0. So find the mass of the melted ice, assume the mass of the cup is small and that it absorbs a negligible amount of heat. So the heat lost from the lemonade, So that's going to be the lemonade was at 27 degrees, and that's going to come down. So we've got a change of MC delta T, and you see that your change in temperature on that left-hand side is 0 minus 27, but we're going to use the absolute value. On the right-hand side is the ice, and the ice doesn't change temperature, so there's no MC delta T on the right. All the ice does is melt. So the sentence had said, the ice in the lemonade reached an equilibrium temperature, some ice still remains. It doesn't tell you the final temperature, but that was your clue. So all the ice did was melt. So on the right-hand side, you only got MLF. So you fill in all the bits, your LF, you've got your temperature change, the C for lemonade. The 0.32 is how many kilograms of lemonade you had. And the final answer is your mass is 0.11 kilograms. And yeah, that's it. That's all you had to do in this one. So the trick of these is setting up the original equation right, but it's not hard after that at all. Here's another one. If you do enough of them, they'll get easier and easier. Here we have 12 grams of ice is added to water in a cup. So it's an aluminum cup. And they don't say ignore the aluminum cup, so we have to take that into an account as well. The ice is going to get warmer. The water and the cup are going to get colder. The system reaches an equilibrium temperature of 20. Find the initial temperature of water. So equilibrium temperature of 20, initial temperature of water. So the water must have been warmer than 20. The ice went in and it ended up at 20. So you just know that part from the logic of things here. We've got what was lost. The aluminum and the water have lost heat. They're getting colder. And the ice is gaining the heat. So that's how you know what to put on the left and what to put on the right. You've got the aluminum, MC delta T, the water, MC delta T. On the right-hand side, you've got ice is going from -8 to 0. So that's MC delta T. Then you've got the ice melting. That's like getting over that hump. That's MLV. So that's the latent heat of, actually, that's supposed to be F, MLF of fusion. So then you've got the ice from 0 to 20, and you've got MC delta T for that. So once this is expanded, and you put in all of the parts that you know, and then you get an answer of the change in T is 4. So if the change in T is 4, you could use logic or you could use an equation, but that means that the final temperature is 20 and it changed by 4. The initial temperature must have been 24. All right, so although in this equation here I had MLV, that should have been an F, this was filled in properly, 33.5 times 10 to the 4. And that is the final one on calorimetry. You'll find lots of ones like these on your assignment. That's it.